Hello, everyone, and welcome. I'm excited to start this journey with you today. Today's presentation is all about the thermal properties of matter. We'll explore how different materials respond to heat, including concepts like heat transfer, specific heat, and thermal conductivity. So let's dive in and discover what makes matter tick when it comes to temperature and heat. Let's explore the fundamental concepts of heat transfer and temperature today. We start with heat itself, which is the energy transferred between objects due to a temperature difference. Understanding heat is essential because it drives all three main methods of heat transfer: conduction, convection, and radiation. Next, we have temperature, a measure of how hot or cold an object is, which provides the basis for understanding thermal energy transfer. To quantify temperature, we use different temperature scales, with the Kelvin scale being absolute, starting from absolute zero, the lowest possible temperature where all molecular motion ceases. Speaking of absolute zero, it's a critical concept because it defines the 0 point on the Kelvin scale, which is essential for scientific calculations. Moving on, the law of thermal conductivity describes how well a material conducts heat, which varies from one material to another. Related to this is the steady state of temperature, where heat transfer occurs without any change in temperature over time, indicating a balance in thermal energy flow. Now, focusing on how heat moves through different processes, conduction involves direct transfer through a material, while convection is a bulk movement of fluid that transfers heat. Convection has specific characteristics, such as being influenced by fluid flow and temperature gradients. Radiation, on the other hand, transfers heat through electromagnetic waves and doesn't require a medium. Its characteristics are unique because it can occur across a vacuum, unlike conduction and convection. Finally, understanding the law of thermal conductivity, the characteristics of convection and radiation, and the conditions for steady state all help us grasp the overall summary of heat transfer methods, which is vital for many applications in science and engineering. All right, let's talk about temperature. Temperature is essentially how we perceive the hotness or coldness of an object or body. It's a key concept because it tells us about the thermal state of a system. Now, from a scientific perspective, temperature is actually a measure of the translational kinetic energy of the particles within that system. So, when particles are moving faster, the temperature is higher, and when they move slower, it's lower. This connection between particle motion and temperature is fundamental because it helps us understand how heat is transferred and how thermal energy behaves. Throughout this presentation, you'll see how this concept ties into various principles of thermodynamics and energy transfer. So, understanding temperature as a measure of kinetic energy really forms the foundation for grasping more complex thermal phenomena. Let's take a closer look at the units we use in temperature measurement. The SI unit for temperature is the Kelvin, which is denoted by the symbol degrees K. Unlike Celsius or Fahrenheit, Kelvin is an absolute scale, meaning it starts at absolute zero, the point where there is no thermal energy left in a substance. This makes Kelvin particularly useful in scientific calculations and thermodynamics because it provides a clear, standardized way to measure temperature differences and absolute temperatures. Understanding these units helps us communicate temperature-related data accurately across different fields and applications. So, whenever you see degrees K, remember it's the SI unit that helps us quantify temperature in the most fundamental way. Heat is the energy transferred from a body at higher temperature to a body at lower temperature. Essentially, when two objects are at different temperatures, heat will naturally move from the hotter one to the cooler one. This process continues until thermal equilibrium is reached. The key point here is that heat is not just a form of energy, but specifically the transfer of energy due to temperature differences. Understanding this transfer is fundamental to grasping how energy moves within physical systems. So, in our overall discussion of energy transfer, recognizing what heat is helps us see how temperature differences drive many natural and technological processes. The SI unit for energy is the joule, and this is a key point to remember. The joule is the standard measurement we use globally to quantify work or energy. It's important because it provides a consistent way to communicate and compare energy values across different contexts and disciplines. Throughout this presentation, understanding the joule helps us grasp the scale of various energy phenomena. So, whenever you hear about work done or energy transferred, think of the joule as that universal unit that ties everything together. Let's start by understanding the relationship between calories and joules. 1 kilocalorie, which is often just called a calorie in nutrition, is equal to 4,186 joules. This conversion is key when we're working across different systems of measurement. Now, to clarify what a kilocalorie actually is, it's defined as the amount of heat energy needed to raise the temperature of 1 kilogram of water by 1 degree Celsius. This is a very practical way to measure heat energy because water's properties are well understood and consistent. In terms of smaller units, 1 calorie equals 4.186 joules. This smaller unit, the calorie, represents the energy required to increase the temperature of a specific mass of water by 1 degree Celsius. When we talk about caloric content, we're essentially referring to this amount of energy needed to heat water. It's a fundamental concept in understanding energy transfer, especially in many biological and physical processes. So, these definitions and conversions help us connect the concept of heat energy with measurable quantities, which ties into the overall theme of understanding energy in different forms and systems. On this slide, we see that at constant volume, when the temperature change is 0, we denote this as delta equals delta C. This means there's no temperature change occurring under those conditions. Conversely, at constant pressure, if the volume change is 0, it indicates a different scenario where the temperature at which this happens is significant. Now, this brings us to an important concept. The temperature at which an ideal gas reaches 0 kelvins is called absolute zero. This is the lowest possible temperature, where particles would be at their minimum energy state. To express temperatures relative to this absolute zero, we use the Kelvin scale. So T equals Tc plus 273.15 kelvins. This conversion links the Celsius temperature to kelvins, allowing us to measure temperature on an absolute scale. Remember, the Kelvin scale is fundamental in thermodynamics because it starts at absolute zero and is directly related to the energy of particles. Overall, understanding absolute zero and the Kelvin scale helps us grasp the absolute limits of temperature and energy in thermodynamic systems, which ties into the broader theme of how gases behave under different conditions. Now, here we see a column of fluid that changes height depending on the surrounding temperature. Warmth causes it to expand, while coolness makes it contract. This visual helps us understand how temperature can be represented physically. The numbers assigned along the height of the column serve as a temperature scale, giving us a way to measure these changes precisely. Each division or mark on this scale is called a degree, represented by the symbol degrees. These degrees are the units we use to quantify temperature, making it easier to communicate and compare different temperature readings. This concept is fundamental because it shows how physical changes in a fluid can be used to measure temperature accurately, which ties into the broader theme of understanding how we quantify and interpret thermal variations in the world around us. All right, let's look at an interesting temperature equivalence. Degrees C is actually the same as degrees F. This is a unique point where the two scales meet. Now, as a quick reminder, 100 degrees C is the boiling point of water, which corresponds to 212 degrees F. And similarly, 0 degrees C is the freezing point of water, or 32 degrees F. These key points are essential because they help us understand how temperature scales relate to real-world phenomena like water changing states. Throughout this presentation, we're exploring how different temperature scales are defined and interconnected, and these points serve as fundamental reference markers. Conduction is the transfer of heat by the direct contact of the particles of matter, meaning that heat moves through a material when the particles themselves transfer energy to their neighboring particles. Essentially, it's the movement of heating particles as they collide and pass on their energy. This process is most effective in solids because their particles are tightly packed together, allowing heat to flow easily from one particle to the next. Understanding conduction helps us see how heat travels through different materials, which is a key part of the overall theme of heat transfer. So, in summary, conduction relies on direct contact and particle interaction to transfer heat efficiently. Today, we're looking at what we call the steady state of temperature. Essentially, this is the point where the heat coming into the material equals the heat leaving it. In other words, the rate at which heat is absorbed by the material matches the rate at which heat is evolved or lost. This balance is crucial because it indicates that the temperature remains constant over time, even though heat transfer is ongoing. Understanding this steady state helps us analyze how materials behave under different thermal conditions, which is key for designing efficient systems. So, in summary, the steady state is that specific temperature where heat absorption and heat evolution are perfectly balanced, ensuring stable thermal conditions. Now let's look at some key concepts related to temperature gradients. First, we have the distance between two consecutive layers, which we denote as d. This is simply the space separating one layer from the next. Next, we have θ2, which is the temperature of the second layer, and θ1, the temperature of the first layer. These temperatures are measured in Kelvin. The temperature gradient, or Tg, is then defined as the difference between these two temperatures, θ1 minus θ2, divided by the distance d. In other words, it tells us how much the temperature changes per unit length along the rod. Understanding the temperature gradient is crucial because it helps us quantify how heat flows through a material. When the gradient is steep, heat transfer occurs more rapidly. Conversely, a gentle gradient indicates slower heat transfer. Overall, the temperature gradient links the change in temperature directly to physical distance, which is fundamental when analyzing thermal behavior in materials or systems. So let's talk about the thermal conductivity of a material. This property essentially describes how well the material conducts heat. In other words, it tells us how easily heat can pass through the material. This is a crucial concept because it impacts how materials are used in various applications, from insulation to heat exchangers. Understanding thermal conductivity helps us choose the right materials for specific purposes, especially when controlling temperature is important. Throughout this presentation, keep in mind that thermal properties like this are fundamental to designing efficient and effective systems. Let's start by examining how the amount of heat flow depends on the distance between two layers. As the distance increases, the heat flow actually decreases, which means they are inversely proportional to each other. So, if you double the distance, the heat flow halves. We can express this as Q being proportional to 1 divided by D. Next, consider the temperature difference between those two layers. The greater the temperature difference, the more heat flows from the hotter to the cooler layer. This relationship is directly proportional, meaning if the temperature difference increases, the heat flow increases proportionally. Then look at the effect of time. The longer the heat flows between the layers, the more heat is transferred. So heat flow is directly proportional to time. If you double the time, you double the amount of heat transferred. Finally, the cross-sectional area of the layer plays a crucial role. A larger area allows more heat to pass through, making the heat flow directly proportional to this area. So, increasing the cross-sectional area results in a proportional increase in heat transfer. All of these points tie into the broader concept of heat transfer and how different factors influence the rate and amount of heat flow between layers. Understanding these relationships helps us grasp the principles behind thermal conductivity and heat transfer efficiency. The SI unit for thermal conductivity is joules per meter Kelvin second, or J per MKS. This might look a bit complex at first, but it really helps us quantify how well a material conducts heat. Now, moving on to the formula shown here. Q equals K times A times the difference in temperature, θ1 minus θ2, multiplied by T over D. This formula is fundamental because it describes the heat transfer rate through a material. Q represents the amount of heat transferred. K is the thermal conductivity, which tells us how good the material is at conducting heat. A is the cross-sectional area. The larger the area, the more heat can pass through. The term θ1 minus θ2 indicates the temperature difference across the material, essentially the driving force for heat transfer. Then we have T over D, where T is the time, and D is the thickness of the material. This ratio indicates how the heat transfer depends on time and the thickness of the material. Thinner materials or longer times increase heat transfer. Connecting this to our overall theme, understanding this formula helps us design better insulation or cooling systems by choosing materials with the right thermal properties and understanding how heat flows through different structures. It's all about controlling and optimizing heat transfer in real-world applications. Let's talk about insulating materials and their importance. First, thermal insulators are used to prevent heat loss to the environment, helping us keep things warm or cold as needed. For example, in everyday life, we use insulation to save energy and maintain temperature. Heaters, on the other hand, are typically made from good conductors of heat. Metals like copper and aluminum are common because they transfer heat efficiently, making them ideal for heating appliances. Now let's look at the thermos flask. It contains a double-walled glass vessel with a vacuum between the walls. The vacuum plays a crucial role because it prevents heat transfer through conduction or convection, keeping your drink hot or cold for longer. In safety lamps, we see a different application. The flame is covered with a cylindrical chimney made of iron gauze, which is a good conductor of heat. This design helps dissipate heat and prevent the flame from igniting flammable gases in the surrounding environment, enhancing safety. Finally, when it comes to insulating materials like glass, coal, thermocol, felt, and sawdust are good examples of bad conductors of heat. These materials are used specifically because they resist heat flow, helping to preserve low temperatures or prevent heat loss. All these examples show how understanding the properties of different materials allows us to control heat transfer effectively, whether to insulate, contain, or dissipate heat in various practical applications. Convection in liquids also occurs because of differences in density. When parts of a liquid become heated, they tend to become less dense and rise, while cooler, denser parts sink. This creates a circulation pattern that transfers heat throughout the liquid. Convection occurs because currents flow when hot gas rises and cool gas sinks. This movement is driven by temperature differences, and it's a natural way for heat to transfer from one area to another in gases. In gases, convection happens because the gas expands when heated. As the gas heats up, it expands and becomes less dense, causing it to rise, while cooler, denser gas sinks. This process helps distribute heat more evenly in the atmosphere or any gaseous environment. It's important to remember that convection is a transfer of heat energy from a part of the body or system at a higher temperature to a lower temperature, and it does this without the particles themselves moving in a bodily sense. Instead, it's the movement of the fluid or gas that carries the heat along. So, in essence, convection is all about the movement and circulation driven by temperature differences, whether in liquids or gases. It's a fundamental process that helps explain how heat gets transferred in many natural and engineered systems, connecting directly to our overall understanding of heat transfer methods. Almost all devices designed for convection include fins for this purpose, because fins increase the surface area that contacts the fluid. Convection heavily depends on this surface area, meaning that the larger the area in contact with the fluid, the more heat can be transferred. That's a key point to remember because it directly impacts how efficiently heat moves away from or toward a surface. Additionally, convection is inherently directional, which means heat transfer occurs predominantly in a specific direction, often from hot to cold. Understanding these characteristics helps us design better cooling or heating systems by optimizing surface area and directionality to improve overall heat transfer efficiency. Let's consider air ventilation through an open window. This is a simple example of natural convection, where air moves due to temperature differences and gravity. When the window is open, warmer air inside tends to rise and escape, pulling cooler, denser air in from outside to replace it. This process helps circulate air naturally without the need for fans or other external devices. It's a great illustration of free or natural convection, which relies on natural forces rather than mechanical ones. This concept ties into our overall discussion on how different types of convection are used to manage heat transfer effectively in various settings. Let's take a look at some common examples of cooling and ventilation methods. First, we have the refrigerator, which is essential for preserving perishable foods by maintaining a cool environment inside. Moving on, proper ventilation in the room is crucial for maintaining good air quality and removing excess heat and humidity. Next, we have the air conditioner, a popular device that cools indoor spaces efficiently, especially during hot weather. Alongside that, electric fans help circulate air, providing a breeze that can make a room feel cooler and more comfortable. We also have hot air blowers, which are useful for heating purposes, but in the context of cooling, they emphasize the importance of controlling airflow and temperature. By understanding these examples, we see the different ways we manage indoor environments, whether cooling them down or ensuring proper airflow. All these methods connect back to our overall goal of creating comfortable, healthy spaces. Radiation is a form of heat transfer that happens through electromagnetic waves. Unlike conduction or convection, it doesn't need a medium like air or water to transfer heat. Instead, it can occur across the vacuum of space. Thermal radiation specifically refers to electromagnetic waves, including visible light, that are emitted by objects because of their temperature. The key point here is that the hotter an object is, the more thermal radiation it emits. So, when we think about how the sun heats the earth or how a fire radiates heat, we're talking about this process of radiation in action. This concept ties into the overall theme of heat transfer methods, highlighting how energy can move in different ways depending on the circumstances. Now, let's look at some practical examples of how the characteristics of radiation are applied. You see, hot water pipes are painted black because black surfaces radiate heat more effectively, meaning they lose heat faster and help in controlling the temperature. Conversely, white cloth absorbs less heat, which makes it more comfortable to wear during summer months because it reflects more heat away from our bodies. When it comes to cooking, the bottoms of vessels are often kept dark and rough. This is because such surfaces are excellent absorbers of heat, ensuring more efficient cooking. And then we have natural sources of thermal radiation, like the electric fan or the sun. These are prime examples of how radiation can transfer heat over distances without any physical contact. Overall, understanding these characteristics helps us design better heating and cooling systems, and also explains everyday phenomena around us. Now, let's briefly review the different methods of heat transfer we've discussed. First, radiation. Radiation is quite fascinating because it involves the transfer of heat without any medium involved. It happens directly through electromagnetic waves, making it the fastest method. You can see this process in action with the heat from the sun, electric bulbs, or even fire radiating out into space. It's unique because it doesn't need air or any other material to carry the heat. Next, we have convection. Convection involves the transfer of heat energy within fluids. This includes liquids and gases. It's a bit more time-consuming compared to radiation because it requires a medium. In this process, heat moves from a hotter part of the fluid to a cooler part, but importantly, this transfer happens without the particles themselves moving bodily. Instead, the entire fluid moves, creating currents that help distribute the heat. Finally, conduction is the transfer of heat through direct contact. This process occurs in solids, where particles are tightly packed. Heat moves from the hotter region to the cooler one through particle vibrations and collisions. Unlike convection, conduction involves actual movement of particles, but it's generally a slower process compared to radiation and convection. So to tie it all together, these three methods, radiation, convection, and conduction, are fundamental to understanding how heat moves in different environments. Each has its unique characteristics and plays a vital role in various natural and engineered systems. Recognizing these differences helps us better control and utilize heat transfer in practical applications.